Thank you, and welcome everyone. I really see a lot of faces, so I appreciate you coming out. What we're going to do today is go through basically what amounts to an experience report of what we've been doing with Go, at least on one project at Comcast. And despite the sort of morbid title here, I promise there's a happy ending. So we're going to talk about streaming video on demand for cable TV with Go. Here's what we're going to talk about. Just a few basics so we know we're all talking about the same thing, some of our performance requirements, our implementation experience when we first started working on it. But of course, we ran into some challenges that dealt with the Go scheduler and timers, so we'll talk about that and how they work. Based on that, we'll talk about how we improved the efficiency of our process, some results, and what comes next. So, video on demand basics. I'm sure that you've all used some form of video on demand in the past. You know what the customer experience is like. You choose what you want to watch, you press play, and you get your show. But there's a lot more than that going behind the covers, right? There's several different ways you might get video on demand delivered. You might download the video to your device, watch it later. You might use a progressive download, which is when it starts showing as soon as you have enough in the buffer, and when the buffer runs dry, you get buffering and you curse the screen. You have adaptive streaming, where when the bandwidth runs dry, you start to see like the really pixelated video. And then you have just straight streaming, where somebody's just shipping the data at the right rate, but you need a reliable network for that. We're fortunate in the cable industry to own our own network, so that's what we do. But it also comes with some constraints. Set-top boxes, we don't plan for them to have big buffers, so we have small buffers that we're dealing with on the at the client side. And that means that we need to have an accurate and stable delivery rate for our data. With a small buffer, if you don't deliver packets fast enough, the buffer runs dry and the decoder starves and your picture will freeze. And if you go too fast, because we deliver this with UDP, the packets just get dropped, and if you don't have the packets you need, you don't get the right video. So we need to make sure this little buffer always has just enough in it, but not too much. And we have a lot of customers, so of course it needs to be scalable. I believe at peak usage, we're at about 1 million video on demand sessions across our footprint, simultaneous. So we of course have clusters and all that sort of thing. So here's what the data path might look like. The software I'm going to be talking about today we call the pump. It sits at the middle of our picture here. And what it does is it retrieves video data from a local cache running on the same server. We're not in the cloud. This is not serverless. This is real hardware. It's doing HTTP requests from the cache, about 1 megabyte chunks of video. And of course, the cache doesn't always have what it wants, so we have a local internal CDN that we run ourselves that gives us the data. So we have these big chunks, 1 megabyte at a time, coming into the pump, and its job is to chop it up into little bitty packets and send them out over our cable QAM network, which is what eventually puts it on a coax cable and it comes into your house and hits your set-top box. So let's look at what our performance requirements are. Like I said, we're running this on bare metal. Our machines have 28 hyper-threaded cores, so we have 56 CPUs. Our target capacity, we need to be able to deliver about 16 gigabits per second at peak load out of one server. Typical single stream will be 4.5 megabits per second bit rate, which means that we need to support 3,500 concurrent streams on one server. Packet sizes. We're running in a standard Ethernet kind of network that has a MTU of 1,500 bytes per packet. MPEG transport stream, the standard video delivery format, amazingly has these tiny little 188 byte packets, but we group up 7 of them into one UDP packet that's 1,316 bytes. So that's what the pump is sending out, is these little UDP packets, 1,316 bytes per piece. So let's look at what our rates would be with that. So that means we need to deliver 427 UDP packets per second for each video stream. That's 1 packet every 2.34 milliseconds. So we're on a kind of short timeline here. One CPU on this box will be supporting 63 simultaneous streams if we've balanced the load right, which is 27,000 packets a second, or 1 packet every 37 microseconds. So, we got to be pretty quick. So here's a little bit about our experience implementing this system. We started simple, as we all do, engineers, good engineers. What's the simplest thing that could possibly work, right? One go routine per stream, one rate limiter per stream. Its job is to know how much time has passed since the last packet. Is it okay to send another packet? Because we don't want to go too fast. But also, maybe we're falling behind. Let us know if we need to send more quickly, right? Then we had a time.ticker for each one of these that was waking up the go routine every so often, ask the rate limiter, and if it's time, we send a packet. So that was the initial implementation. And with Go 1.9, when this story starts, we found that we could not deliver the full capacity we needed to from one server with a single pump running on that server. So there was some engineering work to figure out what are our options, and they tried, what if we split it up into multiple pump instances, and that helped. And we found if we ran 5 copies on one server, it could work. And since we were already load balancing work within a cluster, just doing that across more instances on each server within the cluster was not a big change, so that worked out well. Solve the problem, move on, go solve bigger things, right? Make sure we have all the features we need, so forth. But we never really dug into understanding why we had this effect. And then we later upgraded to Go 111. We skipped 110. It's work to prove that a new version still works the way the old version did, and 110 didn't have any new features we needed. And we were busy fixing and fighting our own bugs, so we just skipped it. 111, there were some nice additions to the net package that we actually needed to use, so we upgraded, we started load testing, and we hit a snag. We found that the same code built with Go 111 used more CPU than the version built with Go 1.9. And we didn't know why. But we knew we were close to our CPU budget already at capacity, and if it increased, we were at risk of not being able to support our requirements. And luckily, we have a really good QA team that was doing all this load testing for us, and they were able to find this quickly before we went to production or anything like that. So we also had an environment we could do a lot of good testing in. So, of course, it's times like this you ask, what does pprof say? Pprof is the Go profiling tool, so we ran that on our process at load, and we found the culprit. Runtime find runnable and the things it calls were using about twice the CPU for the same workload with Go 111 than they were with Go 1.9. And we even proved this by going back and rebuilding the old release that had been built with 1.9 and built it with 1.11, and we're able to see a change in CPU. So it wasn't just our code, nothing in our code changed, it was just the version of Go. But we didn't really understand how this could be happening. So of course, Go is open source, which is fantastic. We can dig into it. We can see how it's working. And we can also look at how it's changed over time. So we started looking at what had changed since Go 1.9. And we knew it was in the runtime package, so in particular, we focused on commits to the runtime package between 1.9 and 1.11. And we found this one that seemed to be the only one that might have some scope with what we're doing. We have lots of timers, lots of CPUs, but as the title of the commit here says, the scalability had been improved, which I believed it did. There were benchmarks in the commit message that's showing it had improved. But for some reason, our process was not seeing that kind of an improvement. So why did we see more CPU with our particular use case? And that's when we had to dig into the Go scheduler and how it worked. And of course, it's open source, so we could do that. If you've ever seen a talk or read a blog about the Go scheduler, you'll notice a curious pattern. They always use the same symbols for the different pieces of the scheduler. There's always an M with a triangle. It's a machine or a single OS thread. Oh, and we have Daniel Morsing to thank for this. I think his article about the scheduler in 2013 set the standard, and everyone's just followed the pattern. GoRoutines in circles, and P, the processor, in a square, which is the data structure that maintains the list of runnable GoRoutines that the scheduler can pick from. And you need to have all three of these together in order for Go code to be running. So let's take a look at the beginning state for a program you might write on a machine where Go max prox equals 4, which would be the default if you have 4 CPUs. I don't have room for 56 Ps on my slide, sorry. But at the beginning of your program, when main is about to start, the runtime has already created all the Ps it's going to use for your process. But it lazily creates threads and GoRoutines on demand, so we just have one M and one G, and main is about to start. And there's some data structures on the P that are important to note for this demonstration. The run queue and the run next. Run next is this special extra slot in the run queue that will be the very next Go routine to run when the current one ends. It's also where a new Go routine will go when it's first created. It kind of jumps the queue, and anything else goes into the bigger run queue. And this is a design intentional to help optimize certain Go use cases where you're sending messages between two Go routines quickly so that they don't keep going to the end of the queue and having to wait longer to communicate with each other. There was a talk by the architect of the scheduler, Dmitry Voyakov, about 2 weeks ago at HydroConf. I watched his video at the airport on the way here. He explains all of this in much more detail, but we're just going to focus on this bit here. So what happens if the main Go routine wants to create a new Go routine? How does that work? So it puts a new Go routine, it gets put in the run next slot. And since we have some idle Ps, we'd rather not have this Go routine just wait in the queue here. We'd like to get it running in parallel if we can. So before it goes back to running the Go routine it was running, it calls this runtime function WakeP. And its job, as the name implies, is to wake up an idle P and get it doing some work. But we don't have any threads to run our idle Ps, so it also will create a new M, attach it to one of the idle Ps, and that fires off the process of running the scheduler. It's got to find some work to do now, so it runs find runnable. If you'll remember, that was the function that we were seeing problems with in our pprof data. So find runnable then looks in its local run next, finds nothing, and it looks in the run queue and finds nothing. So it needs to do a process called work stealing. If I don't have any work local, I want to try to get some work from somewhere else in the system. So I'm going to look at my neighbor, but this is another case where run next and run queue are special. It doesn't try to steal from the run next slot right away, because it might steal work that P was about to grab, and you'd end up with a either racy or thrashing kind of condition. So it prefers to look in the run queue initially. And then it looks in another one and another one because it's not finding any work, and it does this 3 more times before it finally resorts on the 4th pass to looking a little bit harder. It'll look in the run queue first and then finally found one. Got it. So it will steal this Go routine away from its neighbor and start running it. But before it starts running it, it doesn't know there might be still more Go routines. In our case, we see they're all empty, but maybe another one just got created, or I didn't look in all the queues. So let's be careful and let's wake up another P. So we start another thread, it runs find runnable, tries 4 times to find some work, it doesn't find any. So it goes to sleep, and the M goes into an idle thread pool waiting to be woken up for other work later. Meanwhile, our 2 Go routines that we have now spread out across 2 of our processors continue doing their job in parallel, and we're happy. So let's take a look at what this might look like if you have more than 2. If you schedule a lot of Go routines. The main process will start one, put it in the run next, call WakeP, create an M, and then keep going and create 4 or 5 more. Meanwhile, the thread we got woken up on the P calls find runnable, and it starts looking around for work. And it finds a queue full of Go routines here. It will actually try to steal half of them. That way we don't steal as often. We get a batch of work, we can go do it, and when we're empty again, we can go back and looking. So it'll steal these two, it puts one in the queue, and it gets one ready to run, but we gotta call WakeP again, wake up a new thread. It calls find runnable. It finds a queue with 2 in it, steals half, that's 1, gets it ready to run, but we gotta call WakeP again. So we wake another M, and the order that it does stealing is randomized, so it won't always look in the same place first. It might look here, find this one, and steal that one. And now we see how the scheduler has spread the work out to get all the CPUs doing work for us. So this is really nice. We get maximal parallelism pretty quick. There's a couple of GoRoutines still in the queue. They'll get to run at some point in the future. So how does this work with timers? I'm going to replace one of our run queues with a timer queue. So we'll just go with 3 Ps for now. The timer queue is where GoRoutines go to sleep. And they're held separate from the Ps and the Ms. And of note, this is how Go19 works. There's only one timer queue in Go19. That's a foreshadowing, by the way. So let's pretend like this third GoRoutine here wants to sleep. So it calls time.sleep, says I want to sleep for a second. It could just put it in the timer queue, but there's a missing piece here. There's nothing that will wake up that GoRoutine when the sleep has expired. So the first time we do this, it also creates this new GoRoutine called the timer proc. So this is a special GoRoutine, special only in the sense that the runtime starts it in the background for you. But other than that, it's just a normal GoRoutine. So it goes through the scheduler just like any other GoRoutine. It gets put on the run next slot of the P that created it. And then the GoRoutine here that's trying to sleep gets put on the timer queue. And the P that it just left starts running the timer proc. And its job is to look for timers that have expired and do whatever's supposed to happen when the timer expires. In our case, waking up a GoRoutine. But it just went to sleep for a second. It's not going to be ready to wake up yet. So the timer proc needs to go wait. So it waits on an OS primitive of some kind to sleep for whenever the nearest timer on the timer queue needs to wake up. And in order to sleep on an OS primitive, it needs a thread to be sleeping. So it takes this M currently attached to the P it's on and kind of goes off on this OS thread, OS primitive to sleep. And just before it goes to sleep, it calls handoff P, which is a lot like WakeP with some slightly different properties. But essentially it turns into the same result. We create a new M on the P that we just left, and then the main thread there that's running timer proc goes to sleep. The P that we left that just has a new thread, of course, calls find runnable, looking for work, finds a neighboring G in an empty or in a run next, copies it over, and starts running it. So we're back to our full parallelism, and the GoRoutine that went to sleep is in the timer queue waiting for its timer to expire. Let's say before the timer expires, the middle G here finishes its work and just exits. So now we have a P with nothing to do, and of course it doesn't want to just go to sleep. There might be work elsewhere in the system, so it runs find runnable. This is the scheduler's workhorse. So it's going to look around for things to do and find nothing. As you can see, all the run queues are empty, and we said the GoRoutine in the timer queue is not ready to wake up. So it lets its M go to sleep in the idle thread pool. After a little bit more time, the timer proc waiting on the thread on the OS primitive gets notified by the operating system, time for you to wake up. And it says, okay, I want to run, but I need a P to run this timer proc code. So it looks around, finds an idle P, and starts using it to run the timer proc. The timer proc says, oh, timer queue, you have a GoRoutine ready to wake up, so I will put you into my local run queue. And then the timer proc looks for the next one, and the queue's empty, so its job is done. And it needs to go back to waiting for a new timer to get created or something, so it takes this M and runs off to go do nothing again for a while. But it calls handoff P again, which triggers the sleeping thread over in the thread pool to wake up and get attached to this P, do find runnable and find work directly on its own run queue and start running it. So this seems maybe a little inefficient. We've got some threads kind of maybe doing some redundant work, but that's okay. It works, it functions correctly, and we avoid blocking threads from running GoRoutines that want to do work just because we're sleeping, which is a lot nicer than like other languages like C++, where you just put a thread to sleep and you've got a thread doing nothing. We're doing a little bit more efficient than that, but maybe not the best. So let's get back to this runtime commit that we found that seemed to impact our performance or maybe would help timers in some way. How did this help? What did they do? What did they change in the runtime to make things more scalable? Well, they sharded the timer queue. Instead of having just one for the whole process, they created one timer proc for our timer queue proportional to GoMax procs. And the result of that is it helps scalability because the timer queue has a lock on the top of it that you have to acquire before you can do anything with it. So if you have a lot of threads all trying to put things to sleep at the same time, they get a lot of lock contention. And by making many of them, you have less lock contention. And this is where it took a while for us to kind of figure out, well, how did this result in more CPU for our process? And tracing through the runtime code, the question was, well, if we can go to sleep faster, what happens next? And the very next part of the scheduler is to look for more work, which involves work stealing, and work stealing can maybe be CPU time. So anyway, we can go to sleep faster, but now more threads are doing work stealing. So we thought maybe that's what's going on. If we can go to sleep faster, the threads spend more time work stealing instead of blocked on a contended lock. So let's make some observations about the scheduler now after having gone through that. It's good at quickly finding a new GoRoutine to run. It's good at keeping available CPUs busy. It also can spin some cycles on the CPU when work stealing is happening and your queues are empty, because it's looking through them all 4 times, and the more of them you have, the longer that will take. The more Ps you have, the bigger your GoMax procs, the more work stealing has to do. And waking up from a timer involves multiple context switches on OS threads, which we all know is not going to be cheap. So aha, now we're starting to get somewhere. This actually helped us understand why we had to run 5 pumps on a server before. Having 5 pumps on the server is our way of reducing lock contention in Go19. We now had 5 timer queues essentially, and we were sending less work to each one because we had load balanced our work across our 5 processes. But also, we had never changed the value of GoMax procs. The default is your number of CPUs. It was still at 56 for all 5 of our processes. So now they're all competing for the same CPUs and kind of overcommitted, right? So that made Go111 slower because we were doing more work stealing on a bigger pool of Ps for each process. So we had this idea. What if we use the GoMax procs value we should have been using all along, which is 12? And we were happy. So we benchmarked that, and performance of CPU usage for our process actually dropped a little bit below where it had been with Go19. So now we could proceed. So good. We've solved our immediate problem, but if you're like me, you're like, I don't know. But we also filed an issue with the Go project that work stealing isn't always great when you have a large number of CPUs and GoMax procs is high. And we gave a lot of data in the report, screenshots of our top and benchmark values from pprof and a program to help reproduce the problem that wasn't our video code, but just something that looked like it. And the first response that I got to the issue that we filed was, hey, what about maybe with Go111, you can just run it in one process now. You don't need 5 processes. I said, well, we tried that. Nope. Doesn't work like you might think. But we still didn't know why not, right? And this is where the gears are turning, and it took time. This is not happening in a week. This was now spreading out over months, we're thinking, like how could this, what could be going on? So we started exploring how could we improve the efficiency of our code. So let's take a look at something that helped us understand a better picture of what we're doing. This is a to-scale drawing of basically what one video stream is doing in our program. It's waking up, sending a packet that takes about 10 microseconds to do, and then going to sleep for 2.34 milliseconds. So you've got this big gap of time where you're doing nothing, which of course is why we can run a lot of these on one CPU, because it can run other streams in the intervening time. But if these times are randomly distributed, there's lots of little gaps, and every one of those little gaps represents going to sleep. So we have lots of sleeps, which means lots of work stealing, which means lots of context switching when you wake up. And that's lots of CPU for nothing. So like, okay, we don't want to do this many sleeps. What if we could do this? What if we could group the work in a way that allowed us to do it all back to back without having to sleep? We would have fewer sleeps, we'd have less work stealing, fewer context switches to wake up, and hopefully less CPU for the same work. So then we needed to figure out how can we make this happen? How can we implement some code that would have this behavior, this property? And we had two ideas. Well, we started with one idea, and then that led to the second. The first idea was, let's see if we don't have so many GoRoutines, not one for every stream. We'll have one for every P, and then we'll just multiplex the idea of a stream, the data structure for a stream, many of those on one GoRoutine, and we can control the scheduling of when they do their thing better. And while we were working on that, we had this one crazy idea that, it just might work. So we'll get to that one, but let's talk about stream multiplexing first. How did this work? What was our idea here? So the idea, as I said, we'll create one packet scheduler GoRoutine per GoMax procs. And then each of the streams will request a time range that they would like to do their next packet. Well, this is the earliest I'm willing to send a packet, and this is my deadline. If I go past that, then bad things happen. But that time range allows the scheduler to look for periods where there's overlapping multiple streams that are all willing to run within some overlapping time range, and we can group them and transmit all the packets for that group without sleeping. And then go to sleep until the next group is ready. So that was our idea. And it took a little while to implement, and while we were doing that, we were learning and thinking, well, if our goal is just to get everything to kind of be grouped in time, what about this crazy idea? What if we just woke them all up at the same time? What if we just round off our wake-up times to the same moment across the whole system so that when timer proc wakes up, it just finds a whole bunch of timers expired at once, dumps them all into the run queue at the same time, into big batches, and then let Go do its thing. How might that work? Then that might be really easy to implement, right? So let's take a look at some results. This is what Go19 looks like when we didn't do anything special, our initial implementation, where the bottom axis, the x-axis, is number of streams, and the vertical axis is CPU percentage use as reported by the operating system. So you can see this thing goes hockey stick at about a third of the way across the screen, which is why we needed 5, right? If you stay on that left-hand edge, you're okay, but as soon as you get to the steep part, that's bad. So when we're running 5, we're okay. It's kind of in that linear portion. But when we switch to Go111, that's what that looks like. So you can see it's higher than Go19 on the linear part, and it goes vertical sooner. And so this is a confirmation based on real data of what we were observing sort of more empirically from the QA team reports. So since implementing this crazy idea of just make everything wake up at the same time was so easy, let's try that. We actually got that implemented like in 15 minutes or something, and this is what that did. So now we don't have this hockey stick behavior, right? It does a much better job of, on the high end of usage, of avoiding a lot of CPU. But we also notice on the left it's actually worse, which was surprising actually and interesting. And that little hump on when you have about 4 streams per CPU is kind of interesting too. I don't quite know what that means, but anyway, this is the real data. And then we got our multiplexed idea finished implementing, and we got that. So now we're better everywhere, and we're nice and linear. So we were really excited about that. So let's take a look, just review pros and cons of our two different ideas here. The multiplexing idea, it's more efficient on all stream counts. I don't have data on my slides for it, but we were also recording, like, are we delivering our packets on time as part of the metrics? And it was actually more consistent than having separate GoRoutines, which was nice too. And the design we came up with was able to handle mixed bit rates. Not all of the streams are exactly 4.5 megabits. Some are different, and it handles that well. We did some testing with that. The downside is it adds complexity to our code. We're basically writing a custom scheduler on top of the Go scheduler. It's special purpose. It's not a lot of code, but it's still something that we need to make sure it's right and that people can understand. It also means, because we have a lot of streams sharing the same GoRoutine, if one of them blocks, they all block. And that's bad. So we have to be careful to write code that does not block anywhere in the packet delivery pipeline. And that's trickier. If anyone's ever had to write like non-blocking I/O stuff, you know that's not always easy. Crazy idea. Simple, one-line change. I mean, literally, we just had to add time.trunc onto our wake-up time, and the rest of the code stayed the same. And the code can still be separate GoRoutines. It can still block on network activity just the way any other Go code wants. The thing that we like about Go, letting us write network servers without worrying about blocking, right? We keep that property. And it scales pretty well within, one pump instance. Those graphs I was showing were for one instance running all the way out to full capacity. The downside is it doesn't handle mixed bit rates as gracefully as the multiplexing approach, because you have to pick some quantum that you're rounding everything off to, and depending on what your bit rate falls within that, it may not always be a nice, smooth transmission of data. And we are not always at full capacity, and it was less efficient on the left-hand edge, so that's not great either. So we decided to go forward with the multiplexing approach because it kind of wins on all measures, except the complexity one. But it's not that bad. We documented it. We have unit tests for it, so it's worth it. So then we started integrating with our production pump, because we were doing all this in a prototype, just a tool to measure the performance. So we found that there was some behaviors on our input side that weren't scheduler friendly either, but now that we knew all about how the scheduler worked, we could fix those up. It wasn't too bad. We just had to batch some things a little bit more and not have individual channel sends for like every packet. It took a few iterations for us to get all the blocking behavior out of our pipeline so that we didn't have one video stream having a delay, getting some data interfering with other video streams. But about 2 weeks ago, we got this all working. We put it in load test in our QA environment. We had a completely cold cache, went to full load, and we only had 40% CPU use on the box for all the pumps, the caching software, everything. This was lower than we'd ever seen before. This is like a fantastic result. So we're really excited about that. So this is where we're at now. A couple of things we can look forward to. How many of you enjoyed Ian Lance Taylor's talk about generics this morning? Yeah, he's a busy guy. He's also working on rewriting timers. But I spoke with him, and it's not going to be there just yet. Go 114 is hopefully where it'll get brought in. So we got at least 6 months or more where we need to not have his great new timers. But it's in a branch, so Tuesday, I checked it out and I tried it. But first, let's go over what does it do? What does it change, or what will it change? Assuming that Dimitri's okay with it and it gets merged. It moves these timer queues directly into the P struct instead of having them be a separate thing, which means we can get rid of the timer proc GoRoutine, and the P and the find runnable can just directly deal with the timers. And there's a new idea about find runnable being able to steal timers from other Ps if a P runs out of work and there's an expired timer on one of its neighbors. Well, I'll take that over for you and do it. But the main result is that it eliminates this context switching when a GoRoutine wakes up. And the benchmark numbers in the commit message at the end, when he finally, it's like a whole series of commits, and he says, now use the new timer code. And it's some of the most ridiculous benchmark numbers I've ever seen. Like one of the time package functions like afterfunc or something, a 99.5% improvement. I mean, have you ever seen that before? Well, so here's the results after I tried his branch with our tool. This is with separate GoRoutines for every stream. The bad one is Go111, and the bottom one is Ian's new timers, without doing any multiplexing or anything like that on our side. So it's got a lot of the properties we were seeing with our implementation. Although, if you look carefully, you can see that his line starts to bend upwards a little at the end. So if we compare it to our implementation, it's almost exactly tracking except right at the end. So I added 2 lines here. One of them is just our code with Go111. That's the blue line, or the blue line. Well, maybe not. No, it's the gray line. Anyway, it turns out that if you combine ours with Ian's, it's a couple of percentage points better, and it stays a little flatter. But in general, they're pretty much comparable, mostly in the noise, comparable to each other. So would that let us just get rid of our code when Go114 comes out? Maybe, but there's another thing our multiplexing approach lets us do. We now have in our control a bunch of packets ready to send at a time we know, and instead of looping over them and sending them individually, we could potentially call this method from one of the golang.org/x/net packages that lets us send multiple packets with one system call on Linux. And an order of magnitude fewer system calls sounds good to me. But we haven't tried it yet, so that's next, so we'll see. Thank you.